Now, before we actually go back to the taxi example and try to solve the recurrence relation, I want to take a little aside. So here's a question. Suppose to have a set that has precisely n elements, right? How many different subsets can I find that have exactly k elements? Okay, so this is similar to a question we did before. You remember we counted the number of subsets of a set of cardinality 10, where each subset had exactly 3 elements, right? So this should be similar to what we've seen. Okay, so here's the first part of the answer. If k is greater than n, then the answer has to be 0, right? For example, let's say that I have n is equal to 3, right? So I have a, b, and c, right? That's my set S, okay? Then I want something that has 4 elements, right? And of course, there's no way to do that because I can put A here, B here, C here, and what goes there? I can't. So that's a partial answer, okay? What else do we know? Well, otherwise, then I'm going to let A be an element of S, okay? And I'm going to define C of nk to be actually the answer I'm looking for. So C of nk is the number of subsets of size k that I can make out of a set that has n elements. Okay, so here's what we'll do. Okay, I can, for example, choose A, right? So I'm going to leave A, right? And then what we're saying is this: there are C of n minus 1, k minus 1 subsets of size k that have A in them, right? So what we're saying is basically C plus A plus C of n minus 1, k minus 1, right? In this particular case, let's say that k is equal to 2, right? So I already picked A. I only have one more element to fill in, right? There's just one more element. And what can I fill it from? Well, from n minus 1 things, right? I can only pick it from B and C. So I have to select one of these. So that's where this comes from, right? If I chose A, then I can only select k minus 1 elements, and I'm selecting them from the k minus 1 remaining elements of S. Okay, so yeah, that's part of the answer, right? And what if I don't choose A, right? Well, going back to this, let's say I don't choose A, then I have, well, I still have n minus 1 elements to choose from, right? I had A, B, and C. I'm taking A away, so there's only 2 left, B and C. But now I need to select all k from those, right? Because I didn't choose A. So what I have is 2 slots that I need to fill in the ABC case. Okay, so put this together, right? Because basically the subsets either have A or they don't have A, right? Those are 2 different things. And we end up with this answer, this recurrence relation that says C of nk is equal to C of n minus 1, k minus 1. That's assuming that I picked A, and so now I need to fill in k minus 1 elements. Oh, plus, right, if I don't pick A, then I'm still choosing from everything other than A, that's n minus 1 elements, and I still need to choose k things, right? So there's my recurrence relation. Those are all the different ways that I can do this, okay? Now, just between you and me, we usually don't write C of nk, right? We usually write it like this, parentheses nk, and we pronounce that, okay, n choose k, okay? So that's our typical notation. Okay, now I've introduced that, and I want to tie that into another kind of mathematical idea that we have, okay? Because here's the relation, right? So here's 3, okay? And the way that I get it is by adding the number that's directly above and the number that's a little bit to the side, right? So let's take 10, this 10, for example. I'm adding this 6 and this 4. How about this 5? I'm adding this 4, this 1. So you see, every element in this triangle, I can actually get the value just by going up and diagonally, okay? And notice everything else is 0, and that's important because, for example, how do I get this 1? Well, I go up, I get 0 plus 1, so I get a 1, okay? This is just kind of a useful triangle that has that same recurrence relation, right? And just to remind you, C of nk is C of n minus 1, k minus 1, plus C of n minus 1 k, right? So k, that's going up, right? And k minus 1, that's going diagonally, right? So it's that structure. That's how it looks, okay? Now, this particular recurrence is actually fairly old, and one of the ways of drawing it is like this. And the reason people like drawing it this way is that now if you look at any given element, you simply go diagonally up, add those two numbers, and you get, so 6 and 4, that gives me that 10. Now, it's the same as we had before, right? We used to have a triangle that looked like this, and all we did is kind of sheared it so that it now looks like this, okay? That's all that happened. But this is a famous triangle. This is called Pascal's triangle, right? And you may have seen it as what happens when you take, for example, x plus y cubed, and you end up with x cubed plus x squared y plus xy squared plus y cubed. And then the question is, what are the coefficients? And you basically read them off of this row. Here's the 3, right? That's why we picked that row. We end up with 1, 3, 3, 1, right? Those are the coefficients. So Pascal's triangle is pretty famous. You probably saw it in middle school. And it's showing up here, okay? It's kind of mysteriously.